In this video, we will try to prove the Shoelace formula, which is used for finding the area of any polygon if we know their coordinates. And we will try to prove it using Green's theorem, which you might have learned in like calculus 3, right? Which helps us change the circulation integral to the integral of a curl over the domain, something like that, right? Okay, so first of all, let's see what Shoelace formula is. Okay, the Shoelace formula is something like this. So let's say you are in a coordinate system and you have a polygon, right? Let me make a polygon. Polygon should have a straight side, polygon should be bounded. It can be concave or convex, doesn't matter. But yeah, this is a typical polygon. And we have its coordinates x1, y1, x2, y2, x3, y3, x4, y4, x5, y5, and x6, y6. If we have that, like using Shoelace formula, we can find its area. The area will be equals to half of, and then there will be something. First of all, let me just write these coordinates in a systematic manner, and I will put the formula next. So x4, y4, x5, x5, y5, and then x6, y6, and also we need to write the first number, right? And then it's so much like just taking the determinant. It's actually a determinant, but here I will just say it like this. So what you do is you go like the Shoelace. So first of all, you take this product minus this product, and then again after that you take this product minus that product. Again after that you take this product minus that product, and you just go on like that, right? So let me just make this beautiful. Just two more. Okay, so that it looks like a Shoelace, right? So it does look like Shoelace, right? The way it's tied. So the formula becomes x1 y2 minus y1 x2 plus x2 y3 minus y2 x3 plus x4 y5. Oh, sorry, did I miss x3 y4? Okay. X3 y4 minus y3 x4 plus x4 y5 minus x5 y4, right? Plus x5 y6 minus y5 x6. Am I doing it correct? Yeah, I think I'm doing it correct. Yeah. Wait, is it x5 y6 minus y5 x6? Yeah, I think that's correct. Plus x6 y7 minus y6 x7, right? Okay. And oh, we don't have x7, so the last number should be x1. So x6 y1 minus x. Oh, what did I write over here? This should be y6. Sorry, that should be y6. Okay, so x6 y1 minus this becomes y6 x1, y6 x1. Okay, so this is the formula for finding the area. Okay, and I will just demonstrate this once because many people might not believe it. So I'll just do a demonstration and then we will go to proof. Okay, so let's say if we have a rhombus here, let's say, I mean, it's kind of a square. Like I will make a square actually, which is just tilted. And let's say its coordinate is, this one is 2, 1. And then I will go one step right, one step up, 3, 2. And then 2 step up, 2, 3. And one step left, one step up. So this will be 1, 2. Yeah. Okay, so this is one step left, one step up. So basically all of these are root 2, root 2, root 2. Yeah. And then this is also root 2. Am I correct? Yeah, all the lengths are just root 2, right? Okay, and then these are also 90 degrees. You can actually check that. And its area will be root 2 times root 2, which is 2, right? So let's see what Shoelace formula gives us. This will be area half, and then let me write the coordinates in order. 2, 1, 3, 2, 2, 3, 1, 2, and the last coordinate should be the first coordinate, so 2, 1. And then this will be half of, okay, 4 minus 3 plus 9 minus 4 plus 4 minus 3 plus 1 minus 4, right? So this will be half of 1 plus 5 plus 1 minus 3, which is half of 7 minus 3, which is half of 4, which is 2, right? So we see that this actually gives us the area, and this works, right? And now let us try to prove. So let's take the same figure and we will try to prove it. Okay? Yeah. And we will use Green's theorem to prove it. Okay, so also let me name some paths. Okay, let me make this directed like, let me make these line segments directed, right? And let's say this is gamma 1, this is path gamma 2, this is path gamma 3, this is path gamma 4, this is path gamma 5, and this is path gamma 6. So collectively, this whole thing is just path gamma, okay? This whole thing. Okay, so now what does Green's theorem say? The Green's theorem says that if I, let's say, want to take a double integral, so let's go with single integral first. So if I, let's say, want to take a single integral over a path, right? And if it's p dx plus q dy, so basically a vector function pq dotted with the dr, right? The derivative of the r vector dx dy. So basically this is kind of the circulation along the path, right? So if I want to calculate that, so what I can also do is I can actually take the integral of the curl, and the curl will be dq over partial x minus partial p over partial y. So this curl over the entire domain, right? So the in this case the entire domain means this whole domain, right? And over here the curl means like something like the swirl, right? So if you add up all these swirls, so what you get is you get the circulation along the path. So basically the circulation along the path, how is this vector field is changing along that path, right? So yeah, that this is Green's theorem, and we will use this. So we don't really need to know a lot of like the intuition behind this, but just this formula, Green's theorem. Okay, now notice that you can use this formula to actually find the area of the polygon, right? So basically, if this D, so D represents the bounded region, okay, bounded region. So basically, I can also say it as D represents the region bounded by path gamma, okay, bounded by path gamma. So in this case, that will just be, in this case, D will just be equals to the polygon, right? So inside of polygon, right? Inside of polygon. Okay. So and like that means if I find like the integration of dA over this domain, that will just be area of polygon, right? Okay. So here our goal is clear. So we want to make this thing just one, right? Yeah. And one of the ways we can do it is we can also just choose q to be x and p to be 0. If we do that, we just get partial q partial x minus partial p partial y is equals to 1 minus 0. That's 1. You can also choose like q is equals to 0, p is equals to minus x. That also give you 1 minus minus 1, which is 1. But right now, we will choose q as x over 2 and p as minus x over 2. And that will give us partial q over partial x minus partial p over partial y to be half minus minus half, which is 1, right? So we will choose this q and p. And for this q and p, the right hand side will just be the integral over the domain of 1 dA, which is just the area of polygon, right? So we'll choose this q and p. So let's see Okay, so let's see that what the left hand side becomes. So that means for this QNP, the right hand side is just 1 dA, which is equals to the left hand side is the integral over the path gamma of P, which is just minus x over 2, and then dx plus q, which is just x over 2 dy. So this becomes half of the gamma over gamma, and then oh wait, I'm sorry, because this p, there's this partial p partial y, this should have been minus y over here. Similarly, it should be minus y over here. Yeah, because otherwise we don't really it will just go to 0, right? I'm sorry for that. And then this will be, or p will be minus half y over 2, right? I'm sorry for that. Okay, so this becomes over the gamma of x dy minus y dx, right? Okay, so basically to find the area of polygon, we can just evaluate this path integral now, right? And like I think that should not be too hard. So let me again copy this figure over there below. Okay. Yeah. So now for the path integral, we can actually break this path integral into like multiple path integrals, right? So I can write this as sum from I is equals to 1 to 6. There are 6 such paths, and we can just sum over all the paths, right? So we can actually do that because like that's just there's just a rule you can check in the calculus textbook. Like if the paths are adding up, like this path integral plus this path integral, so like adds up to total path integral. So that's why. So this becomes x dy minus y dx, right? Now to calculate this integral, so I will just show you how to do let's say over gamma 1, and everything else will be similar. So x dy minus y dx, right? So what you can do is first of all parameterize this curve, right? This curve. So along the curve, you will notice that along the curve, uh, x will just be x1 plus x2 minus x1 t, right? Where t goes from 0 to 1, and y will be, so y1 plus y2 minus y1 of t. So what I'm trying to do is write this path in terms of t, okay? And then so the 0 x t goes from 0 to 1, right? So this is how x and y will depend on t. And then also notice that because this path is a straight line, so dy will just be y2 minus y1, and dx will just be uh, x2 minus, or you can also see it as like, instead of just dy, let me see, you can see it like dy over dt being y2 minus y1, right? And that will give you dy as y2 minus y1 times dt. So that's what I'm saying. And dx will also just be x2 minus x1 times dt. This is solely because these are straight lines, so slope will just be the normal slope, right? Okay, I mean, like normal slope, I mean slope of the line formula. Okay, so let's do the integral now. So we want to do the integral gamma over 1 of x dy minus y dx. So that means this path is now, I can write this as t going from 0 to 1, right? And x is x1 plus x2 minus x1 t. dy is y2 minus y1 times dt. We will write dt at the end later on. And y is, let me make up some space over here. Let me write this over here. Let me read this over here. This looks good. Yeah, I think that looks good. Okay. So minus, and then we're here y1 plus y2 minus y1 t, and dx is x2 minus x1, and then dt, right? So let's just evaluate this integral. So this becomes integral from t equals to 0 to 1. So first of all, x1 y2 minus y1 plus x2 minus x1 y2 minus y1 t minus y1 x2 minus x1, and then again minus y2 minus y1 x2 minus x1 t and dt, right? Now notice that second and the last term cancel out, and we have these remaining two terms. Again, they also simplify. We have x1 y2 minus x1 y1 minus y1 x2 plus x1 y1 dt. Again, x and y1 cancels out, so we just have integral from t is equals to 0 to 1 of x1 y2 minus x2 y1 dt, and this integral will just be x1 y2 minus x2 y1. Okay, so this was over the path gamma 1 of x dy minus y dx, if I'm not wrong. Okay, but we know that we know that the area of polygon was actually this thing, right? The area of polygon was actually this thing. So I just found out the integral over the path gamma 1, but it's same for all the paths. So what will happen is that, so over all the paths, so we will have the same thing, and what we will have is we will have this thing over here. This will be our result. So basically xi yi plus 1 minus xi plus 1 yi, right? Now over here, okay, in this sum we will also have y7 x7, which are not the coordinates, so x7 should be just x1 and y7 should be just y1, right? Because over here in this figure, like after x6 there's again x1 y1, right? After x6 y6. So if this is how they are should be defined, and yeah, this is the formula, area of polygon, right? And this formula exactly corresponds to what we did earlier, right? So this formula is exactly the same thing. x1 y2 minus y2 x1 plus x2 y3 minus y2 x3 y2 plus x3 y4 minus y3 x4, and then so on, right, up to x6 y1 minus y6 x1. And this is the same thing, like x1 y1 x2 y2. You notice x1 y2 y2 y1 x. Sorry, I have this should be y1 x2. I'm sorry, I just read this formula so wrong. Okay, y1 x2, yeah, and then x3 y3, right, x2 y3 x3 y2, yeah, okay, it's the same thing, right? So finally finally we have verified the formula that we used in the beginning. Okay, so area of polygon. So yeah, this is proved. I just wanted to circle back to the beginning, so that's why I wanted to write this, just to make sure we make a full circle. But yeah, this is the idea. The idea is that using Green's theorem, you can actually find the area of a domain, right? Yeah, by choosing some specific q and p, in this case x over 2 and minus y over 2. And then with this q and p over q and p, you can now go back to the path integral using Green's theorem. That's the main thing. And then you can now easily do the path integral by first of all parameterizing in terms of t using the straight line equations, and then just doing the integral, which will give you the well-known Shoelace formula. That's all, and it's pretty beautiful. There are other derivations too, but this one is actually pretty beautiful in the sense that it gives us an application of Green's theorem, like somewhere that we may not even think of, right? And I found this beautiful. I hope you found beautiful too, and maybe you might want to share it with your friends or something like that, or just enjoy this beautiful result. That's all. I look forward to seeing you in the upcoming videos too.